Which of the following does not have a horizontal asymptote? 4 choices. In the exam, you can guess one of them. It's 25% chance of getting the right answer. Or you can take a look at first choice. Well, before you actually take a look at the first choice, let us briefly recall what a horizontal asymptote means. So, horizontal asymptote is when you go to infinity and you let x go to infinity or minus infinity, and you have a function which is bounded. So let's say you go to infinity and your function looks like this. Or you go to minus infinity at some point and your function looks like this. And so on and so forth. There's a multitude of examples. But the key idea here is that we take the limit as x tends to plus or minus infinity. If we get a number, then this is the asymptote which the function tends to. If we don't get a number, let's say we get infinity or minus infinity or a limit that diverges, then in that case we don't have an asymptote, a horizontal one. So let us take a look at this one. This is the limit. And if we're going to infinity, it means that we're looking at the fastest growing functions. So we can direct our focus on the fastest growing functions. And for this, I want to summon a certain fact which we've used multiple times already. And that is the logarithmic functions grow slower than any polynomial. And if I want to make use of this fact, this is a logarithm and this is a polynomial. So this grows faster. And so there's actually not a problem if I write down x. And now it's a race between log x to the 7th and x. But we don't know what happens with log x to the 7th. But we can use the property of the logarithm to write this power outside as a coefficient of the log. And now we have something we can deal with. Well, guess what? We're going to use the same fact again now. So we have log of x and x. Which one grows faster? It's x. So x dominates the expression. And because x is dominating the expression, we're dividing a small number by a very, very, very big number. And so this expression actually goes to 0. So the limit is equal to 0. And to our luck, it happens to be that we have the exact same case here. So it's log of absolute value of x divided by x. So in that case, the limit, as x goes to infinity or minus infinity, in the absolute value of f of x, I won't write the expression because that'll take us too much time, would be simply also 0. That is because x dominates. Maybe I will also write this here. Well, actually, I didn't write it, but you know what I mean, of course. And then we have 2 more choices. So now your chances have gotten much better. You have a 50% chance of getting the the final grade, which is the whole point for the question. And you have number C. All of these are non-zero. This is given by this fact. So what does it mean for us? Well, not really much. We also take the limit as x tends to plus or minus infinity of this expression. So just like that. But then it's the same concept that we've applied here. Since all of these terms are slower, we can just remove them. By slower, I mean that x grows slower than x squared grows slower than x cubed, and x cubed grows slower than x to the fourth, and so on and so forth. Okay, that, I think that was an accidental rhyme, and I of course do not make these things up. So we have this, we can focus on the biggest terms. And if this is in x, in n, and this is also in n, so it's the same power, what we actually have is that we can cancel them out, and we get an over bn. And I want you to notice that a common feature of the first three choices is that this limit exists and it has a value. This is always the theme. Now, this is an divided by bn simply because we take the limit as x tends to infinity of two constants. Well, the constants are not going to change, they're constants. And the xn's just cancelled out with each other now. And we got rid of the slower terms because in the end we want to focus on the fastest terms. It's like two teams in one race, but each person is racing individually. Then if you want to know which team will win, you need to just focus on the bigger players, which in that case they are xn and xn. These are analogies. If you're not a fan of analogies, that's totally fine. I'm not a fan of analogies either. Just so you know. So the theme here again, this is a constant, and that is a constant. Which means that probably this is the answer. But can we check this? We should be able to. Okay, it's a problem. We'll also use the, you could say, the dual fact to the fact that we had up there. By up there, I mean here. And this fact is e to the x, which happens to be the inverse of ln of x, grows faster than any polynomial. And if that is true, then no matter what we have downstairs here, this e to the x will always win. And since we have the absolute value of x, we don't have to worry about the minus infinity limit. So if I take the limit as x tends to infinity, that's easy. That's easy because we know e to the x will dominate, so this actually goes to infinity. But if I take the limit as x goes to minus infinity, well, it's actually the same thing because you have e to the absolute value of x. So it doesn't really make a difference. It also goes to infinity. You could write positive infinity, for example. And we have never mentioned this before, so this is a new fact. But the reason why e to the x grows faster than any polynomial is because e to the x is an infinite polynomial. So if you think about it for a moment, this is a finite polynomial. And by this we mean that we have x to the m. So its degree is x to the m. It has m terms with different powers of x. Well, actually m plus 1, because you count 0, which does not have any x to 0, which does not have any x per se. But e to the x is infinite. So you could think of this as us expanding e to the x, and we have infinitely many terms. So we have, for example, something of the form x to the m plus 1 inside of there. And for any m, we can find an x to the m plus 1. That's a feature of infinity. So no matter how big this number is, because we have infinitely many numbers in e to the x as an expansion of a polynomial of this type, then we can always find an x which has a degree higher than whatever degree that will be given to us. This is a topic of Taylor series, which is something we will discuss later in the course.